Title: Stretching Each Dollar. Diffusion Training from Scratch on a Micro-Budget. Abstract: This paper aims to address the bottleneck in the development of large-scale text-to-image (T2I) generative models by demonstrating low-cost training. The authors propose a strategy that randomly masks up to 75% of image patches during training, reducing computational cost without significant performance degradation. They also incorporate the latest improvements in transformer architecture and identify the critical benefit of using synthetic images in microbudget training. The model achieves competitive fit and high-quality generations while incurring 118 times lower cost than stable diffusion models and 14 times lower cost than the current state-of-the-art approach. Introduction: The cost and effort of training modern visual generative models remain high, with some previous works successfully scaling down the computational cost. However, the computational cost of even the state-of-the-art approaches remains very high, requiring more than a month of training time on the leading 8x100 GPU machine. The high training cost and the dataset requirements create an inaccessible barrier to participating in the development of large-scale diffusion models. Methodology: The authors consider vision transformer-based latent diffusion models for text-to-image generation. They propose a deferred masking strategy that preprocesses all patches using a patch mixer before masking, thus significantly reducing the performance degradation with masking. This strategy is superior to model downscaling in reducing computational cost. The authors also incorporate the latest improvements in transformer architecture, such as the use of mixture of experts layers, to improve performance and further identify the critical benefit of using synthetic images in microbudget training. Results: Using only 37 publicly available real and synthetic images, the authors train a 1.16 billion parameter sparse transformer with only $1,890 economical cost and achieve a 12.7 fit in zero-shot generation on the COCO dataset. Notably, their model achieves competitive fit and high-quality generations while incurring 118 times lower cost than stable diffusion models and 14 times lower cost than the current state-of-the-art approach that costs $28,400. The authors aim to release their end-to-end training pipeline to further democratize the training of large-scale diffusion models on microbudgets. Qualitative evaluation: The authors provide a qualitative evaluation of the image generation capabilities of their model, 512 x 512 image resolution. They examine diverse style generation capabilities using prompt image of an astronaut riding a horse in style, with following styles: origami, pixel art, line art, cyberpunk, and Van Gogh Starry Night. They also compared training cost and fidelity, measured using FID for zero-shot image generation on COCO dataset, of all models. The proposed research introduces a novel deferred patch masking strategy to reduce the computational cost of training diffusion transformers. This approach pre-processes all patches using a lightweight patch mixer before masking, allowing non-masked patches to retain semantic information about the whole image. This strategy enables reliable training at high masking ratios and achieves better performance compared to existing state-of-the-art masking approaches and model downscaling. The research also explores the impact of combining synthetic images with real images in the training dataset, finding that this combination significantly improves image quality and alignment with human visual preferences. The proposed approach is demonstrated to achieve high-quality generations from moderate-sized datasets in microbudget training. The methodology section provides a background on diffusion-based generative models and diffusion transformers. It explains the forward-reverse process-based approach used in diffusion models, where the forward process corrupts the input data and the reverse process tries to reconstruct the original signal. The section also discusses the use of time-dependent Gaussian noise and the formulation of the sampling process as a stochastic differential equation. The research highlights the importance of parameterizing the score of the density function using a denoiser and training the denoiser using a loss function. It also discusses the use of classifier-free guidance to increase alignment between input captions and generated images. The section concludes by introducing latent diffusion models, which are trained in a lower dimensional compressed latent space, and diffusion transformers, which consist of hierarchically stacked transformer blocks. Key contributions of the research include the proposal of a novel deferred patch masking strategy, the demonstration of its effectiveness in reducing computational cost and improving performance, and the exploration of the impact of combining synthetic images with real images in the training dataset. The research also provides a detailed description of the methodology used in the proposed approach. Equations and algorithms discussed in the research include the ordinary differential equation, ODE, formulation of the diffusion process, the stochastic differential equation, SDE, formulation of the sampling process, and the loss function used to train the denoiser. The research also discusses the use of a variational autoencoder for image-to-latent encoding and its reverse mapping in latent diffusion models. Figures and tables are not explicitly mentioned in the provided text, but the research likely includes visualizations and numerical results to support the proposed approach and its evaluation. The research concludes by highlighting the potential of the proposed approach for efficient and effective training of diffusion transformers. The computational cost of training diffusion transformers is a significant concern, particularly when dealing with large-scale datasets. To address this issue, researchers have explored various approaches to minimize the computational cost while maintaining performance. One common approach is to reduce the sequence size, which is proportional to the number of patches derived from an image. This can be achieved by using larger patch sizes, patch masking, or a combination of both. Patch masking involves dropping a large fraction of patches at the input layer of the transformer, which can significantly degrade performance. To alleviate this issue, researchers have proposed using an auxiliary auto-encoding loss to encourage representation learning from masked patches, known as masked DIT. However, this approach requires optimizing a surrogate objective and has nearly identical computational costs. An alternative approach is to use a deferred masking strategy, where patches are masked after being processed by a patch mixer. This approach is analogous to naive masking but uses a patch mixer to pre-process the patch embeddings before masking. The patch mixer is a lightweight transformer that fuses the embeddings of individual patches, allowing non-masked patches to embed information about the whole image. The deferred masking approach is trained using a loss function that combines the diffusion training loss and a masking loss. Unlike masked DIT, this approach does not require optimizing a surrogate objective or hyperparameter tuning between two losses during training. Additionally, the patch mixer simplifies the overall design and does not require an additional loss function. To further improve the performance of the backbone transformer, researchers have leveraged innovations in transformer architecture design, such as mixture of experts, MO, layers and layer-wise scaling. These techniques increase the parameters and expressive power of the model without significantly increasing the training cost. The proposed approach achieves comparable performance to the baseline unmasked pre-training, even with a high degree of patch masking. However, a small degree of unmasked fine-tuning after masked pre-training can mitigate any undesirable generation artifacts due to patch masking. Overall, the deferred masking approach offers a promising solution to reduce the computational cost of training diffusion transformers while maintaining performance. The paper discusses the development of a novel image generation model, the diffusion transformer, DIT, which leverages a simplified mixture of experts, MO, layer and a layer-wise scaling approach to enhance performance. The DIT model is designed to operate on all patches in the input image before they are masked, utilizing a lightweight patch mixer and an attention layer for processing caption embeddings. The model only denoises unmasked patches, with the diffusion loss calculated on these patches. The authors used two variants of the DIT architecture, DIT Tiny, 2 and DIT Excel, 2, both comprising a patch size of 2. They replace every alternate transformer block with an 8-expert MO block when training sparse models. The models are trained using the AtomW optimizer with cosine learning rate decay and high weight decay. The authors also use a 4-channel variational autoencoder, VAE, from the stable diffusion XL model to extract image latents and consider the latest 16-channel VAEs for large-scale microbudget training. The paper presents an experimental setup that includes key details on the training hyperparameters and the use of the EDM framework from Karas et al. 2022, as a unified training setup for all diffusion models. The authors use Frechet inception distance, FID, and clip score to measure the performance of the image generation models. They also discuss the choice of text encoder, using the text encoder from state-of-the-art CLIP models, and provide details on the training datasets used, including conceptual captions, CC12M, segment anything, SA1B, and text caps. The authors evaluate the effectiveness of their deferred masking approach and investigate the impact of individual design choices on image generation performance. They train each model for 60K optimization steps with the AtomW optimizer and exponential moving average with a 0.995 smoothing coefficient enabled for the last 10K steps. The results show that deferred masking achieves much better performance across all three performance metrics, particularly at high masking ratios. The authors conduct an ablation study to investigate the impact of various design choices on the performance of their diffusion transformer architecture. They evaluate the effects of different masking strategies, patch mixer sizes, and training hyperparameters on image generation performance. The results show that using a larger patch mixer, higher weight decay, and higher learning rate improve performance. However, increasing the block size in block masking leads to a degradation in performance. The authors also compare their approach with training hyperparameters commonly used in large language models, LLMs. They find that using SWI-glue activation in the feedforward layer outperforms JLU activation, and higher weight decay leads to better image generation performance. However, they observe better performance when using a higher running average coefficient for the AtomW second moment, beta 2, in contrast to LLMs where beta 2 approximately equals 0.95 is preferred. The authors validate the effectiveness of two modifications in the transformer architecture: layer-wise scaling and mixture of experts, MO, layers. They find that layer-wise scaling outperforms the baseline constant width approach across all three performance metrics. However, MO layers only achieve similar performance to the baseline model on a small-scale setup, but significantly improve performance when training on a larger scale for longer training schedules. The authors compare the performance of their deferred masking approach with multiple baselines, including naive masking, masked-it, and model downscaling. They show that their approach achieves better performance than model downscaling under an isoflops budget. They also find that deferred masking significantly bridges the gap between masked and unmasked training of diffusion transformers. The authors conclude that deferred masking is a complementary approach to downscaling transformer size to reduce computational cost in training. They show that deferred masking outperforms network downscaling across at least 2 out of 3 metrics until a masking ratio of 75%. Additionally, they demonstrate that deferred masking acts as a strong pre-training objective and achieves better performance when used with an unmasked fine-tuning schedule. Equations and algorithms discussed in the text include the use of SWI-glue activation, JLU activation, and AtomW optimization with beta 2 approximately equals 0.95. The authors also use a mixture of experts, MO, layer with top 2 routing for 8 experts. The text includes several tables and figures, including Table 1, which compares the performance of layer-wise scaling and constant width transformer architectures, and Figure 6, which compares the performance of different masking strategies. Limitations and future work discussed in the text include the need for longer training schedules to effectively use MO layers and the potential for deferred masking to achieve lower performance at extremely high masking ratios due to information loss. In the realm of machine learning and artificial intelligence, researchers have been exploring novel approaches to enhance the efficiency and performance of diffusion transformer models. One such approach is deferred masking, which reduces the computational cost of training these models by masking a portion of the input image patches during pre-training. This method allows for a larger model size while maintaining an equivalent computational budget compared to training a smaller model without masking. The effectiveness of deferred masking is demonstrated through a series of experiments involving different masking ratios and model sizes. By comparing the performance of models trained with and without masking, it becomes clear that deferred masking can achieve superior performance across various metrics, particularly when combined with unmasked fine-tuning steps beyond the isoflops threshold. Furthermore, the authors investigate the microbudget training of large-scale models, focusing on open-world text-to-image generative models. They train a DITXL2 transformer with 8 experts in alternate transformer blocks, utilizing a two-phase training process. The first phase involves pre-training on 256 by 256 resolution images with 75% patch masking, followed by fine-tuning without masking. The second phase involves fine-tuning the Phase 1 model on 512 by 512 resolution images, again with 75% patch masking followed by unmasked fine-tuning. The computational cost of this training process is broken down in Table 2, showing that the total wall clock training time amounts to 2.6 days on an 8xh100 GPU cluster. This micro-budget approach enables high-quality image generation capabilities, as demonstrated through comparisons with previous works across multiple quantitative metrics. In conclusion, the research presented here highlights the potential of deferred masking and micro-budget training for enhancing the efficiency and performance of diffusion transformer models. These findings contribute to the ongoing development of more effective and cost-efficient machine learning algorithms, ultimately paving the way for further advancements in the field of artificial intelligence. The benefits of incorporating synthetic data in training micro-DIT models are examined, with a comparison between models trained on real images only and those trained on a combination of real and synthetic images. Under canonical performance metrics, both models achieve similar performance, with FID scores of 12.72 and 12.66, and CLIP scores of 26.67 and 28.14, respectively. However, qualitative evaluation reveals that the model trained on the combined dataset achieves better image quality, with the real data model often failing to adhere to the prompt and hallucinating key details. To automate the evaluation process, a human visual preference metric is used, leveraging the GPT-4o multimodal model as a proxy for human preference. The results show that images from the combined data model are preferred in 63% of comparisons, while images from the real data model are only preferred 21% of the time. This demonstrates the benefit of additional synthetic data in improving overall image quality. The dimension of latent space is ablated by training micro-DIT models in 4 and 16 channel latent space, respectively. Contrary to expectations, using a higher dimensional latent space in micro-budget training hurts performance, with the model trained in 4-channel latent space achieving better FID, CLIP score, and gen-eval scores. The performance of micro-DIT is compared to previous works on zero-shot image generation on the COCO dataset. The model achieves a competitive 12.66 FID30K, while trained with 14 times lower computational cost than the state-of-the-art low-cost training method. The approach also outperforms Worstchen, with a 2.5 times reduction in training time when using H100 GPUs. The choice of mixture of experts, MO, layers is also ablated, with the results showing that using MO layers improves zero-shot FID30K from 13.7 to 12.7 on the COCO dataset. The use of MO layers is therefore adopted by default in large-scale training. The proposed approach achieves competitive image generation performance with a significantly reduced training cost, utilizing a deferred masking strategy to alleviate the shortcomings of existing masking approaches. The model is trained on a combination of real and synthetic images, leveraging openly accessible datasets and clip-based text embeddings, which are faster to compute and require less disk storage. The results demonstrate that the model achieves near-perfect accuracy on single object generation and outperforms other models on various tasks, including color attribution. The landscape of diffusion models has rapidly evolved, with modern models trained on web-scale datasets and employing transformer architectures. Recent works have demonstrated the effectiveness of diffusion transformers, achieving better performance than earlier models. The use of synthetic captions has also led to significant improvements in image generation capabilities. The proposed approach builds upon these advancements, utilizing a diffusion transformer and synthetic captions to achieve competitive performance. The training cost of large-scale diffusion models has been a significant limitation, with earlier models requiring high computational resources. Recent works have focused on reducing this cost, employing techniques such as cascaded training and patch masking. The proposed approach adopts a deferred masking strategy, which provides significant improvements in performance across all masking ratios. The model is trained at an order of magnitude lower cost than the current state-of-the-art, achieving competitive zero-shot image generation performance. The limitations of the proposed approach include poor rendering of text and limitations in capturing intricate relationships between objects in detailed scenes. Future work can focus on alleviating these limitations, as well as exploring the impact of dataset choice on performance, data attribution for generated samples, and adversarial interventions in the training pipeline. The proposed approach has the potential to empower more researchers to participate in the training and development of large-scale diffusion models, accelerating research progress in this field. The results are evaluated using the Gen-Eval framework, which assesses compositional image generation properties such as object positions, CO occurrence, count, and color. The model achieves competitive performance on various tasks, including color attribution, and outperforms other models on certain tasks. The proposed approach demonstrates the effectiveness of deferred masking strategies in reducing the computational cost of training diffusion transformers, achieving competitive performance at a significantly lower cost. The paper discusses the development of a new text-to-image model, Phi-3, which is designed to be highly capable and efficient for use on mobile devices. The model is trained using a combination of techniques, including variants of gradients to estimate example difficulty and an ensemble of expert denoisers for improved performance. The authors also explore the use of cold diffusion, a method that inverts arbitrary image transforms without noise, and its potential applications in image generation tasks. Furthermore, they discuss the importance of improving image generation with better captions, highlighting the role of language models as few-shot learners. The paper references various datasets, including Conceptual 12M, which pushes web-scale image text pre-training to recognize long-tail visual concepts, and COCO 700M, a large-scale image text pair dataset. It also mentions the use of loss surfaces of multi-layer networks and the scaling vision transformers to 22 billion parameters. Additionally, the authors discuss the potential of diffusion models to beat GANs on image synthesis tasks and the development of hierarchical transformers for faster and better text-to-image generation. They also reference the use of image recognition at scale through transformers and the scaling of rectified flow transformers for high-resolution image synthesis. The paper concludes by discussing the importance of data filtering networks and the potential of switch transformers for scaling to trillion-parameter models with simple and efficient sparsity. It also highlights the role of Fourier analysis in understanding the properties of diffusion models and the development of scene-based text-to-image generation with human priors. The paper discusses the advancements in deep learning models, particularly focusing on the development of GANs and their convergence to a local Nash equilibrium. It also highlights the use of a 2-time scale update rule for achieving this convergence. Furthermore, the authors explore the concept of classifier-free diffusion guidance and its application in denoising diffusion probabilistic models. In addition, the paper mentions the Open Clip project, which aims to provide a comprehensive library for various clip models. Moreover, it discusses the Mistral 7B model, a large-scale language model designed for efficient processing and understanding of natural language. The authors also delve into the concept of predicting generalization in deep learning models, emphasizing the importance of understanding how well a model will perform on unseen data. They discuss the NeurIPS 2020 competition, which focused on this very issue. Moreover, the paper touches upon the topic of scaling up GANs for text-to-image synthesis, highlighting the challenges and opportunities in this area. It also mentions the use of diffusion models for generating data, emphasizing the need for fast generation methods. The paper further discusses the design space of diffusion-based generative models, exploring various techniques and trade-offs involved in their development. Additionally, it covers the concept of guiding a diffusion model with a bad version of itself, which can lead to improved performance. Furthermore, the authors discuss the use of influence functions for understanding black box predictions, providing insights into how different inputs contribute to the output of a model. They also mention the segment anything model, which is designed for efficient object segmentation in images. Lastly, the paper highlights the importance of mixed precision training with 8-bit floating point numbers, demonstrating its potential for improving model efficiency without compromising accuracy. The referenced papers present a comprehensive overview of recent advancements in machine learning, artificial intelligence, and computer science. The citations cover a broad range of topics, including text-to-image diffusion models, classifier-free guidance, adversarial diffusion distillation, and large-scale datasets for training next-generation image-text models. Notably, the papers by Chitwan Saharia et al. And Guillaume Sanchez et al. Introduce photorealistic text-to-image diffusion models with deep language understanding and classifier-free guidance, respectively. These models have achieved state-of-the-art results in generating high-quality images from text prompts. The work by Axel Sauer et al. Proposes adversarial diffusion distillation, a novel approach to improve the efficiency and effectiveness of diffusion models. This method has been shown to outperform existing techniques in various image synthesis tasks. The Leon 5B dataset, introduced by Christoph Schumann et al., is a large-scale dataset for training next-generation image-text models. This dataset has been used to train various models, including those presented in the papers by Vikash Sehwag et al. And Ali Shafahi et al. The papers also cover various other topics, including generating high-fidelity data from low-density regions using diffusion models, targeted clean-label poisoning attacks on neural networks, and fast and accurate attention mechanisms. The references also include works on large-scale datasets, such as JourneyDB, a benchmark for generative image understanding, and DiffusionDB, a large-scale prompt gallery dataset for text-to-image generative models. Furthermore, the papers by Noam Shazir et al. And Yasha Soldikstein et al. Introduce novel architectures and training methods for neural networks, including the sparsely gated mixture of experts layer and deep unsupervised learning using non-equilibrium thermodynamics. Overall, the referenced papers demonstrate significant advancements in machine learning and artificial intelligence, with a focus on improving the efficiency, effectiveness, and robustness of various models and algorithms. The paper discusses the fast training of diffusion models with mask transformers, focusing on the DIT-Tiny2 and DTexcel-2 architectures. The authors use half-precision layer norm normalization and SWI-glue activation in the feed-forward layers for all transformers. They also apply layer normalization to query and key embeddings in the attention layers to stabilize the training. The learning rate for expert layers is reduced by half as each expert now processes a fraction of all patches. The authors provide an exhaustive list of their training hyperparameters in Table 5, including the default configuration for the diffusion model, with some adjustments to match the standard deviation of their image datasets in latent space. They generate images using deterministic sampling from Hume's 2ND order method with 30 sampling steps. For quantitative evaluation on the Cipher Captions dataset, they use classifier-free guidance of 3 and sample 30K images. The authors conduct all experiments on an 8x100 GPU node, using bfloat16 mixed precision mode. They use PyTorch 2.3.0 with PyTorch native Flash Attention 2 implementation and the Deep Speed Flops profiler to estimate total flops in training. They also use just-in-time compilation to achieve a 10–15% speedup in training time. The authors choose the CLIP model as their text encoder, specifically the DFN5B text encoder, due to its state-of-the-art performance and lower compute and storage requirements compared to T5XXL embeddings. The paper also discusses the cost analysis of training, translating wall clock time to financial cost using a $30 per hour budget for an 8x100 GPU cluster. The authors report a 2.5x reduction in wall clock time on H100 GPUs and assume a $3.75 per H100 per hour cost. They use 5 datasets to train their final models, including conceptual captions, segment anything 1B, text caps, JourneyDB, and DiffusionDB. They construct a text-to-image dataset named Cipher Captions, which closely resembles web-curated datasets and serves as a drop-in replacement in their setup. The paper discusses the development of a new text-to-image model, DIT, which leverages a transformer-based architecture to generate images from textual descriptions. The authors use a dataset of 37 million images with synthetic captions generated by an LLaVA 1.5 model. They employ a VITH-14 model to measure clip scores, selecting images with scores higher than 0.25, resulting in a total of 1.3 million images. The authors compare the computational cost and storage overhead of CLIP and T5 text encoders, finding that T5 embeddings achieve better generation quality but are an order of magnitude slower than CLIP embeddings. They use CLIP embeddings for their dataset due to the high storage overheads of T5 embeddings. The evaluation metrics used include FID, CLIP-FID, and CLIP-score. The authors also discuss layer-wise scaling and mixture of experts, which enable the construction of larger models with minimal impact on training and inference cost. The paper presents several ablation studies to understand the impact of different components on the performance of the DIT model. These include ablations on the choice of beta 2 in the Atom optimizer, weight decay in the Atom W optimizer, parameters of noise distribution, block size in block sampling, size of patch mixer, choice of feed-forward layers, cyclic learning rate scheduler, and learning rate for each batch. The results show that the best performing model uses a beta 2 of 0.999, weight decay of 0.1, patch mixer with parameters m, s, equals 0.6, 1.2, block size of 1, patch mixer size of 384 with multipliers for attention layers, ma, and feed-forward layers, mf, set to 0.5 and 0.5, respectively. SWI-glue activation in feed-forward layers, a cyclic learning rate scheduler with 1 cycle, and a learning rate of 1.6 times 10^4. The proposed mixture of experts (MO) architecture utilizes an expert choice (EC) routing mechanism, where each expert selects the top patches using the importance score determined by the routing network. This approach is favored over conventional routing due to its simplicity, eliminating the need for auxiliary loss to balance the load across experts. The router is implemented as a linear layer and is trained jointly with the rest of the network. The authors conduct an ablation study on deferred masking in patch mixer, observing better performance with higher learning rates. However, training instabilities arise after approximately 2 case steps, despite using QK normalization and mixed precision training. It is recommended to ablate the choice of learning rate for each network and use the maximum attainable value without causing training instability. A fast training strategy using cyclic learning schedules is also considered, but only marginal benefits are observed. The authors also investigate the effect of masking on performance, shifting from random masking to retaining a continuous region of image patches with block masking. The results show that any amount of block masking degrades performance compared to random masking of each patch. This is likely due to the redundancy in visual information between neighboring patches, and the diffusion transformer model receiving more global semantic information about the image with random masking. The authors demonstrate the effectiveness of their approach through generation results on the gen-eval benchmark prompts. The model trained on real data only is compared to the model trained on combined real and synthetic data. The results show that the model trained on combined data generates more diverse and realistic images. The use of identical random seed for generation ensures a fair comparison between the two models. The generated images demonstrate the model's ability to capture complex scenes and objects, such as animals, vehicles, and food items. The paper presents a comparative analysis of various text-to-image models, including Raphael, Stable Diffusion XL, Deep Floyd, DALLE2, Ernie VILG 2.0, and PixArt Alpha. The authors showcase the capabilities of these models by generating images based on descriptive texts. On page 29, the authors display a comparison with previous works, featuring images generated from prompts such as a parrot with a pearl earring, Vermeer style, a car playing soccer, digital art, street shot of a fashionable Chinese lady in Shanghai, wearing black high-waisted trousers, and half-human, half-robot, repaired human, human flesh warrior, mech display, man in mech, cyberpunk. These images demonstrate the model's ability to capture complex concepts and translate them into visually appealing images. Page 30 continues this comparison, presenting additional images generated by the models. These include a cute little matte low poly isometric cherry blossom forest island, waterfalls, lighting, soft shadows, trending on ArtStation, 3D render, Monument Valley, Fez video game, a shanty version of Tokyo, new rustic style, bold colors with all colors palette, video game, Genshin, Tribe, Fantasy, Overwatch, cartoon characters, mini characters, figures, illustrations, flower fairy, green dress, brown hair, curly long hair, elf-like wings, many flowers and leaves, natural scenery, golden eyes, detailed light and shadow, a high degree of detail, and cartoon characters, mini characters, handmade, illustrations, robot kids, color expressions, boy, short brown hair, curly hair, blue eyes, technological age, cyberpunk, big eyes, cute, mini, detailed light and shadow, high detail. The paper highlights the strengths and weaknesses of each model, providing insights into their performance and potential applications. By comparing these models, the authors aim to advance the field of text-to-image synthesis and encourage further research in this area. The figures presented on pages 31 and 32 showcase the capabilities of the proposed model in generating images from textual prompts. These images are synthesized using randomly selected prompts from Party Prompts, Yu et al. 2022, a dataset designed to evaluate the performance of text-to-image models. On page 31, Figure 16 displays images categorized into abstract, animals, artifacts, arts, food and beverage, and illustrations. The model demonstrates its ability to generate diverse and coherent images across these categories, highlighting its understanding of complex concepts and objects. Page 32's Figure 17 further expands the model's capabilities by synthesizing images for indoor scenes, outdoor scenes, people, produce and plants, vehicles, and world knowledge. This showcases the model's capacity to generate images that reflect real-world scenarios and objects, as well as its understanding of abstract concepts like world knowledge. These figures collectively illustrate the model's proficiency in interpreting textual prompts and translating them into visual representations. The generated images demonstrate a high level of detail and realism, indicating the model's strong performance in capturing the nuances of the input prompts. The significance of these results lies in their implications for future applications of text-to-image models. Such models could potentially revolutionize various industries, including advertising, film production, and even education, by providing an efficient means of generating high-quality visual content from textual descriptions. However, it is essential to note that while the model performs impressively, there may still be limitations and areas for improvement. For instance, the model's ability to generalize to unseen prompts or its robustness against adversarial inputs could be explored further. Additionally, the ethical implications of such technology should not be overlooked, particularly concerning potential biases or misuse. In conclusion, the images synthesized by the proposed model on pages 31 and 32 underscore its potential as a powerful tool for generating visual content from textual inputs. As research in this area continues to advance, it will be crucial to address both the technical challenges and ethical considerations associated with these models. The research paper presents a novel approach to image synthesis using textual prompts. This methodology leverages the power of deep learning models to generate images that are semantically related to the input text. The authors demonstrate their model's capabilities by showcasing synthesized images from two datasets: Drawbench, Saharia et al. 2022, and Genevall, Ghosh et al. 2024. Figure 18 illustrates the synthesized images generated by the model using randomly selected prompts from Drawbench. These images showcase a wide range of objects and scenes, such as animals, vehicles, and landscapes, demonstrating the model's ability to capture diverse concepts and translate them into visual representations. Similarly, Figure 19 displays images synthesized from Genevall prompts. This dataset includes more complex and abstract concepts, which the model successfully translates into coherent and visually appealing images. The generated images exhibit high fidelity and realism, indicating the effectiveness of the proposed approach in bridging the gap between language and vision. The authors employ a state-of-the-art deep neural network architecture that is trained on large-scale datasets of text-image pairs. This training process enables the model to learn the intricate relationships between linguistic descriptions and their corresponding visual representations. The model's performance is evaluated through various metrics, including visual quality, semantic relevance, and diversity of generated images. A key contribution of this work lies in its ability to handle ambiguous or open-ended prompts, often resulting in multiple plausible interpretations. The model addresses this challenge by generating multiple images for each prompt, thereby capturing the inherent uncertainty and variability present in human perception and interpretation. Overall, this research presents a significant advancement in the field of text-to-image synthesis, offering a powerful tool for applications such as data augmentation, artistic creation, and human-computer interaction. The proposed methodology has the potential to revolutionize various domains by enabling users to create visual content directly from their thoughts and ideas. The paper presents a comparative analysis of various diffusion models, specifically focusing on their ability to generate diverse styles in image synthesis. Figures 2023 showcase the results from different models: Stable Diffusion 1.5, Stable Diffusion 2.1, Stable Diffusion XL, and the proposed model when given prompts that describe complex scenes with specific styles. In Figure 20, the prompt is, "Addressed in a suit posing for a photo in style. Natural lake landscape in background, detailed light and shadow, high detail." The proposed model demonstrates superior performance by capturing the nuances of the prompt, such as the subject's attire and the detailed lake landscape, while maintaining a high level of realism. Figure 21 illustrates the generation of a luxurious with a next-generation modern design. Again, the proposed model excels in capturing the essence of the prompt, showcasing a sleek and futuristic design that aligns well with the given description. In Figure 22, the prompt is, "A moonlit night over a, mysteriously rendered in style." Here, the proposed model effectively captures the mystical atmosphere of the scene, rendering the moonlit night with remarkable detail and realism. Finally, Figure 23 presents the generation of a lush garden full of, vividly illustrated in style. The proposed model successfully captures the vibrant colors and lushness of the garden, demonstrating its ability to generate diverse styles across various prompts. Overall, the paper highlights the proposed model's superior performance in generating diverse styles compared to existing diffusion models. This is achieved through its ability to accurately capture the nuances of the given prompts and translate them into visually appealing images. The research paper presents a novel approach to image synthesis using textual prompts from the JourneyDB dataset, Ghosh et al., 2024. This methodology leverages the power of deep learning models to generate images that are semantically related to the input text. The authors demonstrate their model's capabilities through a series of experiments, showcasing its ability to produce high-quality images based on randomly selected prompts from the test set. Figures 24 and 25 on pages 37 and 38 respectively, illustrate the synthesized images generated by the model. These figures highlight the model's capacity to capture complex concepts and translate them into visual representations. For instance, one prompt might be, "A sunset over a mountain range," and the model would generate an image depicting this scene with remarkable accuracy. The underlying algorithm utilizes a combination of natural language processing techniques to understand the textual input and computer vision algorithms to generate the corresponding image. This interdisciplinary approach allows for a more nuanced understanding of how language influences perception and vice versa. A key aspect of this research is its potential applications in various fields such as advertising, film production, and even therapeutic settings where visual aids can enhance cognitive processes. Furthermore, this technology could revolutionize the way we interact with digital content, enabling users to create personalized visual experiences based on their preferences. However, as with any emerging technology, there are limitations and areas for future improvement. The model's performance may vary depending on the complexity and ambiguity of the textual prompts. Additionally, ethical considerations arise when considering the potential misuse of such technology, such as generating misleading or harmful content. In conclusion, the paper presents a groundbreaking approach to image synthesis that bridges the gap between language and vision. While it has significant potential benefits, it also raises important questions about responsible AI development and use. The research paper presents a novel approach to image synthesis using textual prompts from the JourneyDB dataset, Ghosh et al., 2024. This methodology leverages the power of deep learning models to generate images that are semantically related to the input text. The authors demonstrate their model's capabilities through figures 26 and 27, showcasing synthesized images based on randomly selected prompts from the test set of JourneyDB. In figure 26, the model successfully generates images that reflect various aspects of journeys, such as landscapes, vehicles, and people. For instance, one prompt might be, a train journey through mountains, and the corresponding synthesized image would depict a train moving along a mountainous terrain. Similarly, figure 27 illustrates the model's ability to generate diverse images based on different textual inputs, further highlighting its versatility and effectiveness. The key concept behind this approach is the use of a deep neural network that learns to map textual inputs to visual outputs. This is achieved by training the model on a large dataset of text-image pairs, allowing it to understand the relationship between words and their visual representations. Once trained, the model can take any given text prompt and generate an image that reflects its meaning. The significance of this research lies in its potential applications across various domains, including but not limited to advertising, film production, and virtual reality. By enabling the creation of high-quality images from textual descriptions, this technology could revolutionize how we visualize and interact with information. However, as with any machine learning model, there are limitations and areas for future improvement. For example, the model may struggle with ambiguous or abstract prompts, requiring further refinement to handle such cases effectively. Additionally, the quality of the synthesized images could be enhanced by incorporating more advanced techniques or larger datasets. Overall, the presented approach represents a significant step forward in the field of text-to-image synthesis, offering a powerful tool for generating visual content from textual inputs. As the technology continues to evolve, we can expect to see increasingly sophisticated applications across various industries. The Cipher Captions dataset, an imitation of the widely used CIFAR-10 dataset, was created to facilitate small-scale experimentation on text-to-image generative models. This dataset is a crucial tool for researchers in the field of machine learning and artificial intelligence, particularly those working on image generation tasks. Figure 28 from the research paper showcases selected images with their corresponding real and synthetic captions from the Cipher Captions dataset. These captions are essential for training and evaluating the performance of text-to-image generative models, as they provide a benchmark against which generated images can be compared. The Cipher Captions dataset is designed to mimic the structure and complexity of the CIFAR-10 dataset, which consists of 60,000 images in 10 classes, with 6,000 images per class. By creating a similar dataset with captions, researchers can test and refine their text-to-image models more efficiently, without needing to work with large datasets that require significant computational resources. The use of synthetic captions in addition to real captions allows for a more comprehensive evaluation of model performance. Real captions provide a baseline for understanding how well the model can generate images based on human-provided descriptions, while synthetic captions offer insights into the model's ability to generate images from machine-generated text. Overall, the Cipher Captions dataset is a valuable resource for the machine learning and AI community, enabling researchers to explore and improve text-to-image generative models. The dataset's design and structure, along with the inclusion of both real and synthetic captions, make it an ideal platform for experimentation and evaluation of these models.